Not audible.
Okay, sorry for the interruption. So we'll start from the beginning. So we'll start with the computational models in embedded design. Okay. So in this one, so as we have seen that, so if we take about the different computational models in the embedded design, so basically depending upon the different computations, what you are going to do. Okay, so that particular embedded system you are going to make use of. So if we start with the different design, so the first one which you are going to have is your data flow model. Okay, so the first one is your data flow graph. Second is your control data flow graph. So third is your state machine model. Fourth one is your sequence program model. And fifth is concurrent or communication process model. Sixth one is your object oriented model. So these are the six models which we have to discuss. So now first comes when it comes to the data flow graph model. Okay, so in the data flow graph model, as you have seen, or diagram. So the data flow graph or diagram model. So that we are going to have. So in some book they are going to refer it as DFD. Some book they are going to refer it as DFG. So both are same, data flow graph or data flow diagram model. So now here what it is going to do, what are the requirements, the data requirements is there for that particular, when you are building your embedded system. If that particular requirement, whatever the requirement, data requirement you are going to have, so that if it is represented in terms of graph, so the data processing data processing requirements will be translated into or represented in terms of data flow graph. Okay, it will be represented in terms of data flow graph. Okay, so now when it comes to the data flow graph model, so basically it is a data driven. So what do you mean by data driven? So if that particular graph has to work, it requires the data. So now that particular model is going to be executing that particular program depending upon the data, is determined by the data. So the program execution here is going to be determined by the data. So now it mainly, this particular model depends upon the operation or the data transfer. Okay, so it mainly depends upon the data. Okay, it depends upon the type of the input data which you are going to have. So it depends upon how the transformation is going to take place between input data to output data. Okay, so that is what it is going to have. So indeed, so if you take the data flow graph model, so it's a visual model in which the uh, visual model, so in which the operations on the data is represented using the block circle. Okay, so the operation what you are going to perform, so the operation on the data which you are going to perform, that will be represented by the circle. Okay, so that we will see next. So and the data flow is represented using arrows, as we have as you people already know in flow chart how to write the flow chart. So obviously there will be number of blocks will be there depending upon the type of the operations what you are going to perform. So similarly here also, so if you want to perform some operation, so on what you are going to do the operation, you are going to do the operation on the data, and that particular operation is represented by circle. Okay, so next I have to show how the data is going to flow. Okay, from where to where the data is going to go. So that particular flow of data is represented using the arrows. So that particular data representation, the data flow representation is represented by arrows. So now whenever you are going to have the input, if whenever you are going to have the input data, so whenever you are going to have the input arrow to the process or circle, so that means, so where operation is represented by circle, right? So when you are going to have the operation represented by the circle, so whenever you are going to have the input to that particular circle, so then it is called as input data. And after doing the operation, some output you are going to generate, and it is separated by the outward circle, outward arrow. So and that particular process is called as uh, output data. Okay, so then that is how it will be represented in your data flow graph notation. So now when you are going to have the embedded applications, when you are building your embedded applications which are computationally intensive and data driven or modeled using this particular data flow graph model. Okay, so this is a typical example what we are going to have. Suppose if we take an example of an application containing a computational requirement. What type of computation I'm doing? I'm doing the computation of x is equal to a plus b is one computation I'm doing, and y is equal to x minus c is another computation what I'm going to do. So now first is what I have to generate the x. Okay, first is I have to generate the x. So as we have shown that, which we have seen here. So this is the data flow model which you are going to have. So as we have seen here, so now here, so here what the data flow which you are going to have represented, the operation what this is going to be performed, right? So this is the operation what it is going to be performed. So that is the addition is the operation what it has to perform. That is the computation what it has to do. So if you take here, so this is add operation what it is performing here in this particular circle. That is operation. So if you take this particular node, it is a subtraction operation it is going to be performed, right? So according to the data flow node. So this is this particular circle, it is called as node. So now these are nothing but the input data. So that is A and B. So where you are going to have the this is whenever the input are going to come, so it will be invert to the node. Okay, so and then whatever the result you are going to get, the result which you are going to have, the result is x now. So what is x? X is nothing but a plus b. So x is nothing but a plus b. So that is the result. The result is nothing but it is going to be indicated by outward arrow, as we can see here. So your A and B will be inward arrow to that particular node. That is what type of operation you have to do. For the type of operation, what you have to do, what are the data which you require? What are the data which you require? Okay. So that will be determined by the node. Okay. So next, what is the output you are going to get here? So the output what you are going to get is X. So now your second operation, the computation has to be done. The second computation, what it is doing, the second computation it is doing as y is equal to x minus c. When it is doing the second computation, where it is x minus c, so one of the input is x, which is output of your first node. Okay, so if you take this one as node 1 and node 2, what is happening here? Okay, node 1 and node 2. So now here, so what type of process is happening? So the process it is happening is addition. Okay, so now after that one, the result which you are going to get is X. So that will be fed as an input to this particular process. This particular process, what it is going to do? So this particular node is going to do the process of subtraction. This particular node is going to do the process of subtraction. What subtraction it is going to do? It is going to do the subtraction of X minus C. It is going to do the subtraction of X minus C, and it is going to have the outward arrow, and it is going to have the outward arrow, and which will be resulting in Y. So now whenever you are taking your data flow graph model, okay, so here if you take the data flow graph model, so a data path is nothing but what? It is a data flow path from input to output. So that means here the inputs are what? A, B, and C. A, B, C are the input, and the output is Y. So it is nothing but what? It is nothing but the data flow which is happening from input to the output. So now this particular model is now called as acyclic because it is not forming any cycle, right? So it is not forming any cycle. Since it is not forming any cycle in this particular graph, so it is a acyclic. Acyclic is nothing but what? So whatever the output you are going to get, so that will be fed to the input again. So that is similar to your combinational circuits which you are going to have. Okay, so in your combinational circuit, you are going to have the cycle, right? Because if we talk about the combinational circuit, what will happen? So the output will be fed as one of the input to generate the next output. So here we are not giving any of the output to the input. So that's why it is called as acyclic. So it is A, D, F, G. So if it does not contain multiple values for the input variable and multiple output values from the given set of inputs. Okay, so that is what it's going to have, this particular type of model. So that is about your data flow model. So anybody having any doubt with respect to a data flow model? So it is going to have the process and it's going to have the arrows. Okay, so the block of data operation which you are going to operation on the data which you are going to do. So that is nothing but process. So that will be represented by circle. So and then the flow of data. Okay, so the flow of data is represented by the arrow. That is inward. If it is an input, it is an inward arrow. If it's an output, it will be output arrow. One of it will be described. So the next type of model is control data flow graph. So here you can see it here. So you're going to have the here you are going to have the control flow graph. So in this one, in the control flow graph, what will happen here is 1 minute. As the name indicates, control data flow graph. Okay, so your execution is controlled by data. So the execution is controlled by the data. So now, and it does not really involve any of the control operations. So it does not involve any control operations, but it is controlled by what? But it is controlled by the data. So in this particular, what it means, we'll see next. So it is control operations where it is involved here. So we are telling that it does not involve any control operations or conditional operations, but normally it will involve that one. According to the textbook, they are going to tell that it's not going to make use of the control operations. So normally where depending upon that particular operation or decision making, so it is basically make the use of the decisions. Okay, so control won't be there, but it is going to make use of the decisions. So it is basically used for modeling applications which is involved in the conditional program execution. So where if that particular temperature rises, for example, so what action I have to take? So if this particular temperature is below this particular limit, then what action I have to take? So that when you are going to have this type of embedded applications, like if you take your the input, the air conditioner is the best example what you can take. So your air conditioner, the AC has to work depending upon the outside temperature. Depending upon the outside temperature, the inside temperature also get varied. So there, the decision making has to come into the picture now. So every time I have to check that what is the temperature of the outside of my house. So depending upon that one, I have to control my input. I have to control the temperature of my AC. So those type of applications is going to make use of the control. Okay, so controlled conditional program execution. So now in your CDFG, that is in your control data flow graph model. So both it contains what your data operation also it will contain, both your control operations also it will contain. Okay. So now when it comes with respect to the CDFG, so it since it contains both data operations as well as the control operations. So your data flow graph, so it is going to make use of the data flow graph as the element, one of the element. So it is going to make use of the data flow graph also, which we have discussed previously. Along with that one, it is going to make use of the decision makers. So decision maker is similar to your normal in the flowchart what you have been used, the diamond symbol. So the same diamond symbol you are going to make use of here to make the decisions. Okay, so it is going to be conditional constructs as the decision maker. So now if you have the control data flow graph, so where the CDFG stands for control data flow graph. So it contains both data flow nodes and the decision nodes. So what are the two nodes it contains? So it contains both your data nodes and control nodes. Okay, so you are going to make the decision making, and you are going to do the data operation also. So now, so when you are going to have this type of data graph, then that particular graph is referred as control flow graph. Okay, so now here what will happen? For example, if my flag is equal to 1, I'm taking. So I have to perform x is equal to a plus b. So if a flag is not 1, that will come in else part. So it is going to perform the operation of y is equal to a plus b. So you are going to do some operations. In that particular operation, you are going to have what? So you are going to have some C code, for example, I'm telling. So here, if we take the example, okay, in this particular example, if we take, so I am going to have if flag is equal to 1, some example, x is equal to a plus b is 1 statement I'm going to execute. If it is wrong, so if flag is not equal to 1, I am going to perform y is equal to a minus b is another operation. For that one, I have to write the control flow graph for that one. So now if you take the control flow graph, so normally the control node, so if you take the control node, it's similar to your flow chart. In your flow chart, which your diamond symbol which you have been used, so the same symbol you are going to make use of. So normally the control node which you are going to have, that will be represented by the diamond block. Okay, where it is a decision making element. So this particular block is the control node which is there. This is the decision making, because which data flow, which data node I have to make use of, or which process I have to perform. Okay, so your data flow node is represented by process. So it is going to define that what type of process I have to perform. Now your control node is going to decide that. So which is the addition I have to make it. So your control data flow graph, what it is going to do? So this particular node is going to translate the requirements. So what type of requirements you require? So whether you require the if part or whether you require the else part. So that's it is going to decide. Now from the example what we have discussed, so here what will happen? So if the flag is equal to 1, so if the flag is equal to 1, it will be true part. So if it is this will be true part, this will be false part. Okay. So now if the true part is there, what operation I have to do? That is a plus b. So the data is coming here. So this is a is data input data, b is input data. So that I have to perform the addition data. So this particular node or what type of process it is going to perform? It is going to do the operation of a plus b. It is going to do the operation of a plus b. So this particular data node is going to do. So after that one, it will go to the output. Now, if this particular decision goes false, that means your flag is not equal to 1. If flag is not equal to 1, what will happen? So then this particular node has to execute. So this particular data node or what type of process it has to do, so that will be determined. So what type of process it has to make? So it has to do the subtraction operation. So that means if it is false, what it will do? So it will determine your, so a and b is there, again a minus b, some. So that is x is equal to a plus b or y is equal to A minus B, it is going to perform the operation. So now this particular control data flow graph is there, which is there. So it is going to translate the requirements which are there. So the translate the requirement which is modeled to a concurrent process model. So here, whatever the decisions it is going to make, so this particular decision or which process has to be executed, the process which has to be executed will be decided by the control node. So this is called as control node. Okay. So the process which has to be executed. Okay, the process, that means what type of operation you have to perform. So that is called as process. Okay. So which process you have to execute, that will be decided by whom? That will be decided by the control node. That will be decided by the control node. Okay. So this is one real-time example for modeling the embedded application using control data flow graph. So some of the example is you are capturing and saving the image to a format set by the user in the digital still camera. So sometimes you may have still thread. So this is typical real world application, what they are going to tell. So according to the textbook. Okay. So this is not the mandatory that it has to make use of the same example we have to take. So in the according to the textbook, what they have taken, it is digital still camera. And so what type of format you have to be saved. So you know that it is going to have the JPEG format is there, BMP format is there, and then there are some more formats are there, right? So depending upon the type of the selection which you are going to make, so that type of image is going to be that in that type of format, the image will be stored inside your camera. Okay, so that's what the example what they have given according to textbook. So here, depending upon the condition, the output has to be done. That is, process has to be selected. So that also means what? So your air conditioner is also taken next condition, but why they are not taking is that is event driven. Okay, that is depending upon event means what? Depending upon the previous, it has to continuously sense the temperature. So that will come in the different part in the state diagram. Okay, so that we are going to discuss next. So next, when it comes to the state machine model, so the third one is your state machine model. So now in the state machine model, so it's going to make use of modeling both reactive, used for modeling reactive or event-driven embedded system. So now whose processing behavior is dependent on state transition. So that means what? So this particular state machine model is going to be used for reactive or event-driven embedded system. What do you mean by reactive or event-driven embedded system? What do you mean by react? Can anyone tell? We have discussed already. What is the difference between reactive and real-time system? What do you mean by react? Can anyone tell the answer? Can I have this answer from your side? What do you mean by react? Already forgotten. So now in the react means what? So depending upon the changes, what is happening in the outside world, so your system has to behave. The behavior is going to behave, the system is going to behave depending upon the situation which is acting, which is happening at the outside. Okay, so that is that your AC only is taken as an example, or if you are take uh, your seat belt alarm is the example what they have taken here. So that is also one of the example. So that means due to some event, so that particular embedded system has to start working, and the processor is processing behavior has to change. So that is totally dependent on transactions. Okay. So if you take the, it is basically this particular modeling is going to be used for reactive or event-driven embedded system, where if you take start considering the event-driven or event-driven or reactive, so there the processing behavior is dependent on the state transition. So you are going to have the different transition of the states from one state to another state. Like for example, if I take, I am now sitting, so the sitting is one state. So if I stand, then it will change the state from sit to stand. After standing, I start moving. So from standing to moving, it will become one state. It is like that. So it is going to change the states depending upon the behavior. Okay, depending upon the state processing behavior, the changing of the state is going to happen. So here also what will happen? So typical where this particular type of state machine model is going to be used. So this particular state
So not audible.
Okay, so the event which is going to have, the event is going to be happening. So the state machine model here, so if you take the state machine model, the state machine model basically describes the system behavior. So you can say that the state model describes the system behavior. With what behavior it is going to change, check. So it is going to describe the system behavior of the state and what type of event is going to happen after having that particular event, what action I have to take after taking the action, from which state to which state your transition is going to go. So this particular model describes the system behavior, these things. So one is state, second is event, third is action, fourth is transition. So now what do you mean by state? Is the first one. State is nothing but what? Where your current situation is in. It is a representation of the current situation. So if we take the walking of a person, so in which state that particular person is, whether it is sitting, standing, or what, maybe which state he is in. So that represents the current situation in which state he is in. Now, what is an event? So event is nothing but some input you are going to get to that particular state. So it acts as a stimuli to for state transition. Something happens to that particular person. So for that one, what if you are sitting means what? So someone will come and some parent, if you're in a home, so your parent may come to you and tell you that so go and bring that particular vegetable from the market. Now we are sitting. So according to who is the stimuli who is giving, your parent or mother or father who is giving that one. So depending upon that one, so the input is coming from your parent. So now whenever the input comes, so the what is the input? It is giving the stimulus for you for the stress transition. That means you are sitting now. Your parent is a event. What a parent is coming and it is giving the stimulus. That means he is telling that go and bring the vegetable from the market. So that is some event has been done now. Has been assigned to you people. You that telling that you have to bring the vegetable from the market. Now the transition is going to take. So what's the transition you are going to make? So you are going to, you have been sitting in one place, you have to stand up and you have to take the bag and you have to start moving. Okay, so now transition is what is going from one state to another state. That means if you are sitting, if you are changing from sitting to standing, so it is changing from one state to another state. That is what you are going to have. Okay, so that is you are going to change the state. So transition is the movement from one state to another state. So next is action. So next comes the action. So when it comes to the action, so action is nothing but what? Action is nothing but the activity to be performed by the state machine. So action is nothing but the activity to be performed by the state machine. So it is activity performed by the state machine. So activity, it is activity performed by the state machine. So depending upon the type of the activity, what is going to be done. So what action I have to take. So that will be defined by the action. So these are the four different this system behavior where your state machine model is going to specify. Okay. So next, if I take the finite state model, so it is one of the number of states are finite. So if we take the example in this particular textbook, so they taken the example of your seat belt warning of your car. So because what are the different states it is going to make. So now there's what are the system requirements are captured. So what is the requirement of your seat belt warning? So can I have from your side only? So if you want to have the seat belt warning, so all of you have, most of you are having the car in your home. So now, do you know during what are the scenarios you have faced when that particular seat alarm warning is going to happen? So this is according to the textbook when it is written. So now the technology is advanced. Now the more and more advanced technology is there, and obviously the changes in the seatbelt warning also been changed. Okay, so according compared to the um, description what they were given in your textbook. Okay, so here all of you have censored that one already. So in your seatbelt alarming system. So that is a typical example for your state machine model. So in your what are the basic requirements you are going to have? So if we take the seatbelt warning system, so you are going to have the seatbelt warning system. In the seatbelt warning system, it's an automotive automotive embedded application, which will be used for finite state machine model. So in this one, what are the system requirements you should have? So first, when that particular when that particular passenger seat that is a seat belt warning has to start only when your car is started. So only when your car is started, so you have to start particular process. That means whether you have been put on the seat belt or not, right? So now first requirement is what? The first requirement is what? The vehicle ignition is turned on. Okay, the vehicle ignition is turned on, and the seatbelt is not fastened within 10 seconds of ignition on. That means my car is started, but that particular timer, it will wait for 10 seconds. So in that particular 10 seconds, if you are not uh, wear the seat belt, so then the siren is going to come. Okay, so if you are not fasten that particular wear that particular seat belt, so the system generates an alarm signal for 5 seconds. That is older one. So according to the older one, it will generate the alarm signal for 5 seconds. It was switching off, but now it is not there, right? So in whichever the alarm seatbelt warning you are going to use, so it will be continuously beeping till you wear the seatbelt. That is what the technology now is happening. But according to the textbook, what they were written, so this it was if you are not fastened the seatbelt after the switching on of your vehicle, after 10 seconds the alarm was going on. So that particular alarm was be given for 5 seconds. Again after 5 seconds it was turning off, even if you are not wear your seat belt. Okay, so that was that time, but now it is not that particular scenario. So even if you are now, if you are not wear till that particular time, the siren will be continuously beeping, right? The alarm will be continuously beeping. So now the alarm is turned off when the alarm time expires, or if the driver or passenger fastens the belt or ignite if the switch is turned off, whichever happens first. So, according to here, what they are going to give. So, when your alarm is going to turn off, so the alarm is turned off after the timer expires. So that means whatever the alarm has to be signaled, so that particular alarm will be having some timer. So, if that particular timer is over, so your alarm signal will be stopped. The alarm signal will be stopped. So other when the alarm signal will be stopped, the alarm signal has to stop if you switch off your car. That means if the ignition switch is turned off, so then it has to turn off the alarm signal. Then the third condition is what? If passenger fastens the belt. Okay, either 5 seconds is over, or if the passenger fastens the seat belt, or if the signal if ignition is turned off. So if any one of the event is occurred, if any one of the event is occurred, your alarm has to turn off. So now, what are the different states your finite state machine has to be there now? So here the states are what? Your alarm is one state, alarm off is one state. As you can see, alarm is off is one state. So waiting is another state, and alarm on is one state. So what are the event you are going to have? The event is what? You are going to switch on your car. So that means your ignition key is on. I have to check for whether my ignition key is on. I have to check whether my ignition key is off. Whether I have to check that the 5 second timer is going to off. Whether the alarm thing is going to happen for 5 seconds. So the timer is there for both alarm as well as the timer is going to start. So next, whenever the seatbelt is on, so the timer has to stop. So whenever the seatbelt is on, the timer has to stop its working. So these are the different states where your finite state machine model has to be there. So now next, when it comes to the finite state model, so how it will be represented. So now initially assume that your your alarm is off. Initially, I am going to consider that the alarm is off, as you can see in the left side. Okay, your alarm is off. When it has to change from going from alarm off to the waiting state. So when you are going to, it will go from alarm to the waiting state till your ignition key is turned off, or if your ignition key is on. So when ignition key is gone, it will go for waiting time. That is how much? It is 10 seconds. It will give wait for 10 seconds. That means within 10 seconds you have to wear your seat belt. So your timer will start. That is the period where our waiting period is going to happen. So now it will wait for 10 seconds. So if the timer expires, for the 10 seconds, if the timer expires for that particular timer expires for 10 seconds, so when the timer expires for 10 seconds, your alarm has to turn on. That means it has to give you the indication that you have not wear the seat belt. So that particular timer is going to, after the expiry of the timer, so that alarm has to turn on. So now how much time that alarm has to turn on is the next question. So now I have to go from alarm on to alarm off state. So I have in the alarm on state now. So now the alarm on for, I am going to switch on the alarm for 5 seconds. That means that is going to beep for 5 seconds. Now your alarm or state is there, right? So that will be having one timer. So that timer will start whenever the alarm is started. So when the alarm started, the timer starts. How much time it is going to take? It is going to give you the time of 5 seconds. So after 5 seconds, after the alarm started, so if you are, whether you are not wear the seatbelt or not, that is immaterial. So even if you are, that is according to the case study of this particular textbook. Now it is the different states it will come now. Okay, so that your people know. So that will be contradictory if you are going with the present seatbelt alarm system and the system seatbelt alarm system which have been there in your textbook. Okay, so now your alarm time will not expire itself. This particular alarm time is there, right? So this will not expire itself till you switch on. This till your seatbelt is on. But according to this particular textbook, what will happen? Your alarm will be on for 5 seconds. So if this particular 5 second expires, this particular alarm time expires, then it will go from alarm on to alarm off state. It will go from alarm to alarm off. Now, what are the other state? It will go from alarm on to alarm off state. Whenever, if in between, within this particular 5 seconds, within that particular 5 seconds, if your seat belt, you are going to put it within that particular time. If you fasten your seat belt, then also your alarm should go off. It will go change the state from alarm on to alarm off state. So now another state which is going to have, one is your alarm time expire. It will go from alarm off on to alarm off state, which will be indicated by the arrow. So that is state transition. From which state to which state, the arrow indicates from which state to which state the state is changing. So the state is going to change from alarm on to alarm off for three conditions. Whenever you are going to have the alarm time expires, when you are going to have your seatbelt on, or when you are going to have your car is switched off. That is your ignition key is off. So here you can see it here. The ignition key on event triggers what? 10-second timer. As I told you here. That is a transistor state to waiting. So now if the seatbelt is on or ignition key is off, event occurs during the wait state, the state transition into off state. So here also, when the ignition is on, okay, so if within this particular 10 seconds, if your seatbelt, if you are put it, then also it will go for alarm off state, right? Or if you are going to switch off your car, then also it should go to the alarm off state from waiting state. Okay, so this is what the state transition is telling. So if when it is going from waiting to turn off state, or when it is going from waiting to alarm on state, or when it is going from alarm on to alarm off state, or when it is going from alarm off to waiting state. So that's what this particular diagram is going to specify about. Okay, so anybody having any doubt here now? So this is what the event is going to happen here. So here the alarm or state continues until the seatbelt is on. So the alarm on state is going to be continuous. So that is till your seatbelt is on, or if your ignition key is off, or your alarm time event expires. That is as I told you in the previous slide. So this occurrence of any of these events transitions the state to alarm off state from the running. So the wait state is implemented using the timer. As I told you that the waiting state is implemented by the timer. So that timer is also have certain set of states and events for state transitioning. So the timer model can be shown in the following figure. So you can see when the timer should be idle, or when the timer should be ready, and where the timer should be running. So when you talk about the idle, so initially the timer will be idle. When the timer has to start, the timer has to start whenever you are switched on your car. So the whatever the event, at that particular time when the car is started, you have to load the timer. Okay. So now what's the action? So your timer count will be equal to new count. Okay. So that will be there. So after ready, so it will be in ready state. I will load the timer, how much time it has to wait for that one. After that one, it will start counting. So it will be in ready state now. Okay. So after start timer. So now after after some time, after the ready state, it has to start timer. So what it has to do? So I have given the 10 seconds. It will start decrementing. 9 seconds, 8 seconds, 7 seconds, 6 seconds, and decrement the count. That is action what it is taking. It is taking the action of decrementing the counter. Okay. So now when it is going to have decrement the counter after it becomes 0. Once it becomes 0, so you start from your running is done. So it will go from even stop timer. So when it goes to the 0 seconds, it has to stop the timer. So that means the timer has been expired. So if the timer has been expired, it has to set the flag, set timer flag. So after the set timer flag is happening, the next action has to take place. Okay. So next action is initiated to the other state, but your clock has to go to the idle state now. But since your clock's work is completed, that is your timer work is completed. So it has to go to the off state. So first is you have to load the timer, and when loading the timer count should be new count. So here it will be 10 seconds for your initially when it is going from alarm off state to waiting state. So when it's going from waiting to alarm on state, it should be 5 seconds. Alarm on to alarm off. So it will be giving the timer count as 5 seconds there. So there are two timers we are using here. One is the timer which will start between your going from waiting to alarm on state. So if any of the action you are going to perform within that particular period, whether you have to fasten your belt or whether you are going to switch off your engine, so that has to be taken care. So that is going to be here. So you see from the final state machine, so there are three states which you are going to have, which is idle, ready, or running. So during the normal operations, when the timer is not running, it is set to be in idle state, as you are told. So when it is going to have the ready state, when the timer is loaded with the new count corresponding to the required time delay. So the timer will be there in that particular state until the start timer goes. Okay. So the timer changes from running to the ready state on receiving the start timer event. So you are going to have running from the ready when you are going to have the start timer. That means you have to start counting the time, or that is decrementing the count, and remain in that particular state only, that is in a running state only, until the timer count is expires. That means when it starts decrementing the count, when it reaches the 0, so that has to start the another state, right? So that particular that particular event is going to occur whenever the timer is going to be stopped for a certain duration which you have been fixed. Then again the timer goes back to the idle state from the running state on receiving the stop timer or timer ever expires. Okay. So this is one of the example. What they have taken for your state machine model. So anybody having any doubt till now for today's class? Anybody having any doubt?